We're going to continue looking at how to make decisions with uncertainty by looking at what if we have incomplete information. So we're going to continue the example from the previous videos. We're looking at that decision about whether or not we should do research and development, marketing, and sell our particular product. Now, I just want to show you something as we move into a more complicated decision tree, is that if you are using SchemDraw to create these decision trees, so first in our previous video, we found that not all versions of SchemDraw were working properly. So you can change the version here. We are stable here at 0.17. So if you run it and it is not working without this piece, so if you run it like this and it gives you errors, then you can specify which version of the package to make sure that you have a version that works. We import SchemDraw and we import Flow. Now, when you start to get these really complicated decision trees, they're really big. What you might want to do is, instead of having it try to show in your Python workbook, because it's kind of hard to see all at once, you might want to export it. And so you can export your images from SchemDraw. So what you'll want to do is you'll want to mount your Google Drive, just like we do for so connecting and importing our files. So you are going to be linking your drive. And just while I'm talking about linking your drive, if you are looking for this code, we are here at drsteph.powers.github.io/BIA. We are in this Python workbook called Optimization. Click here, open in Google Colab so that you can work on the workbook yourself. And in our previous videos, we often did the step, where did I go? We often did the step of mounting our Google Drive so that we could bring in our data sets. Well, here we're mounting our Google Drive so we can go the other direction. We can save it to our Google Drive. So you would mount your Google Drive. This is connecting your workbook to your drive. Nobody else has access to any of that. It's your copy of the workbook and accessing your Google Drive for your work. So doing this doesn't give access to anybody else. Once you have mounted that drive, then when we go to create our SchemDraw drawing, we can actually save it to that drive. So here we have, now we have a way more complicated version of our decision tree because we want to add in that we have imperfect information. So we're actually going to create a decision tree that looks like this to represent the fact that we don't actually know some of these outcomes. Perfect information assumes that all information necessary to make a decision is known. And imperfect information says we don't have all the information necessary to make a decision. So maybe we're going to contact some experts who are going to give us some idea as to possible outcomes. We can use our decision tree to model the unknown information, and later we can use Bayes' theorem to model conditional probabilities that say the value of the outcome will depend on if this happens, then that happens, and what's the likelihood that they happen. So first though, let's make our very complicated decision tree. So what we're going to do is we're going to have our new product, and we're either going to invest in research and development or terminate the project. We're also going to look at, if we invest in R&D, we are going to hire an expert. I'm going to make it bigger here. All right, after we invest in R&D, instead of just immediately terminating the project or going on to market it, what we're going to do is we're going to decide, should we hire an expert or should we not hire an expert? If we don't hire the expert, then we have the old decision, terminate the project or market it. If we market it, positive economy, that's my face is hiding, and negative economy. So this bottom piece here is the same one we had before. But we could alternatively say, if we invest in research and development, then we're going to hire an expert, and the expert is going to tell us whether or not they're predicting a good economy or a bad economy. So we hire the expert to help evaluate how well our product is going to do. If we have a good prediction for the economy, then we go to market it. And then the reality is a good or a bad economy. We could also get a good prediction, and then instead of deciding to market it, we terminate the project. So we could say, great, they said it was going to be a good economy, but we're still not moving forward. Or the expert could say there's going to be a bad economy, and we decide then to market it. And then in reality, it can be good or bad. My face is hiding the bad. They could say that it's a bad economy, and then we could decide based on that to terminate the project. So you can see the number of branches and scenarios has gotten quite a lot larger. So we want to turn this into a decision tree. So the first step we do with a decision tree really is to lay out all of the activities, the boxes. To help make it clean, as we mentioned previously, I've actually given it a location on the grid, and this is so I can line up the boxes both on the x-axis and the y-axis to make it look cleaner, because the problem I have with SchemDraw is that it just puts things everywhere, and it's a pain in the ass to try to move and rearrange things around. Really, given the choice, do it in Microsoft Visio to make your flowcharts and decision trees. But if you're going to do it in SchemDraw, which is what we're talking about here, first we load in all the different boxes. So that's what you see here, and they're in the locations I told them to be. And then I need to add my flow. And so just like we had talked about in our previous video, we take the same information and we add in these flow.wire. It's an arrow, and it's going to go from one corner to the next corner and then have that extra text. So in this case, you're specifying the corner of which box, which is why you labeled the boxes A0, A7, A8, and then it's going to go to what corner of the next box. So you can be very specific. But even with this, if you don't first load the boxes, then it doesn't lay things out nicely. So you just go in after you've run the boxes, and then you add in all the lines. The addition I'm showing you here, besides the fact that we just got a much more complicated decision tree, is that you can have it output it. And so I'm telling it where to go. This is because I've connected it to my Google Drive. So this part here is it's telling it to go inside the BIB handbook, inside the chapter 10 folder, call it tree.png. So when I run this, it will show it, but it will also dump a copy into my Google Drive here under the folder BIB handbook. In the folder chapter 10, it'll create a copy. So then when I go to look at it here, see how it's just so huge, it's hard to see. If I just want to see it to be able to zoom out, I have that image in my Google Drive. So I can go in here where it says tree, and you can see the whole thing. And I can then paste it into something else. Okay. So you can actually export it is what I'm trying to show you here. All right, so we've created this giant decision tree. Now we want to do some sensitivity analysis here, recognizing that this time we have incomplete information. So what we're going to do here is we are going to create a table that looks at the predicted good or bad economy and whether it was actually a good or bad economy. Because what we're doing is we're moving into our Bayesian analysis. So in your stats, you talked about Bayes. And Bayes' theorem says there's two events, A and B. The likelihood that A happens if B happens. So this vertical line here is condition. A is conditional on B. The probability A happens if B has happened. That's going to be equal to the probability that B happens if A happens times the probability of A divided by the probability of B. So in other words, the probability of A happening given B has happened is equal to the likelihood of A and B happening divided by the probability that B happens at all. Okay, so this probability that B happens is called the prior probability. So we can convert this for our particular scenario, and we can look at what's the probability of a good economy if our expert predicts a good economy. So here we have good economy conditional on they predicted a good economy. And the top here is the probability that there actually is a good economy. So it's the probability they predicted good, that it's actually good, times the probability that it's actually good, divided by the probability of predicting good. Okay, what does all that mean? All right, what we're going to do is we're going to start out with a table that shows us that this is what actually happened. This is what was predicted to happen. So, sorry, actually happened is the row. Predicted to happen here. What is the probability of these different outcomes? We can then use that to populate our decision tree. Because the part that we didn't see when we zoomed into the decision tree is that, where's my probabilities with my question marks? There we go. Okay. So what we have here is that we have the good predictions. Okay. What we're missing here is these probabilities of a positive economy and the probability of a negative economy. So I don't know if you can see this is a question mark and this is a question mark. Because what is the probability that there will actually be a positive economy if they predict there will be a good economy? And what is the probability that there will be a positive economy, so question mark right here, if they predict a bad economy? What's the probability there will be a bad economy if the expert predicts a bad economy? So what you see here at the end of the decision tree, these last sections here, is we don't know the probabilities of these outcomes. Okay, so we need those conditional probabilities. If they predict good, then what's the likelihood it'll be positive? If they predict bad, what's the likelihood it'll be positive? So we're going to use Bayes' theorem to help come up with those conditional probabilities, because remember, we have incomplete information. We don't actually know the probability of the good or bad economy, so we've hired an expert to help us figure it out. All right, so let's go back here. All right, so how do we start this off? We start this off by doing the information that we do know. So we are going to look at good and bad. And we suppose that we know, and let's see to start, we have our price of 35. We have our quantities high and low. Okay, we're using pandas and numpy for a lot of this initial work here. And what we want to do is we want to look at what's the probability if it's good, what's the probability if it's bad, and are they predicting? So what we know, we would know this information from this expert we've hired, were they accurate in the past? So what we'd say is, okay, well, you expert, how did you do at forecasting previously? And they say, okay, well, in the past, I predicted it was good, and it was good, 80%. Okay. I predicted it was good, I predicted it was bad, and it actually ended up being good, 20%. So see how these equal 100%. So the actual was good, and then they had predicted good 80% of the time, and it was actually good, and they had predicted bad 20% of the time. Now, when it was actually bad, they had predicted that it was going to be good 30% of the time, and they predicted bad when it was actually bad 70% of the time, right? So we can see here, that on the balance, they're more accurate than not, okay? So we're going to use this information here to help inform the probabilities. So we look at, they predicted good when it was actually good, 80%. They predicted bad when it was actually good, 20%. So let's load that into here. So what we're going to do is we're going to look at predicted based on actually good and actually bad. And so here, if reality was good, then they were good 80%. If reality was bad, they were good 30%. So actual good and actual bad. So we're basically creating a little table here, right? Actual good and actual bad. So actual good, actual bad is the second piece here. They predicted good, 80% and 30%. They predicted bad, 20% and 70%. So we'll load that in. We'll turn that into a table because, my goodness, I get so confused by lists. So we're going to have our conditional here, and we're going to use pandas, turn into a data frame, use that list zip, and make a column called predict, a column called for G for good, column for B for bad. We'll call it predict, predict good, predict bad. And we're going to move over to the index, the predict. So what we're going to do is create a table that looks like this, where we can see if it was actually good and they predicted good, it was 80%. And if it was actually good and they predicted bad, 20%. Okay, so we've created this table here. Now, we're going to start with our uninformed. So the scenario here is that if we didn't hire the expert, we were assuming 40% chance of a good economy, 60% chance of a bad economy. So that's our uninformed information. All right, so what we're going to do then is we need to create what is called a prior. Okay. So we need to figure out what is the probability. So if we go back here, see prior is this one on the bottom. And in this case, we need to know the probability that they would predict good, and we need to know the probability they would predict bad. So if our uninformed information is that 40% chance of a good economy and 60% chance of a bad economy, let's look at how we would predict the probability we would predict good. All right, so when we look at the probability that the expert would predict good, what we're looking at here is this column that's related to what they predicted as good. So they are predicting that it's good 80% of the time, and they're predicting good 30% of the time when it's actually bad. So to find the probability that they would just predict good, we're going to take the 40% chance that it's a good economy times that 80% that they're doing correctly and the 30% of the time when they are saying it's good, even though in reality it was bad. For the probability they predict bad, we look at the probabilities, right, that they are accurate when they do that. So they're predicting bad when it's bad versus bad when it's good. And so we're taking the uninformed information of a bad economy happening 60%, and we take that 60% and multiply it times they're saying bad 20% when it really is good, and 70% when it really is bad. So the probability that they predict good is going to be 44%, and the probability they predict bad is going to be 54%. So once we have that probability of predicting good, we can then find the probability of a good economy given that they predicted good. So we need the probability that it's actually good, the probability that they predict it's good, and then that condition of predicted good based on it actually being good. So we're going to take this and we can then convert this information here. We take our 0.8 times 0.4, which is what we had calculated for the first part here. And we are going to divide that by the probability of them predicting good. So we're using our Bayes theorem here to find, so our probability they predict good is going to be 44%. And this top part here, the probability they predict is good when it's actually good. Okay. Probability they predict it's good when it's actually good. That's going to be this 80% times the probability that it actually is good is our 40%. So we get our 73% is they predict good when it's good. And here our probability they predict good when it's bad is going to come from the fact that when they predict it's good and it's actually bad, that's 30%. We're saying that the probability that it's actually bad is 60%. And the probability they predict bad is going to be that 54%. Okay, So you can see how we're getting these different probabilities of what they predicted versus what it actually is. In terms of predicted bad, here we have the probability they predict bad when it's actually good is 20%, times the probability that the bad economy actually happens is 40%, divided by the probability of them predicting bad, which is that 54%. Okay. And so the last one here is the probability that they predict it's bad when it's actually bad is 70%. The probability of a bad economy is 60%. And the probability they predict it's bad is at 54%. And so what we get here with these percentages is that we're using Bayes' theorem and conditional probability to populate. Go back to our decision tree here. These question marks that we have here, that this unknown probability of a positive economy given a bad prediction, a negative economy given a bad prediction, a negative economy given a good prediction, and a positive economy given a good prediction. So we're trying to come up with what these conditional probabilities are using Bayes' theorem. So how do we do this part in Python? We created this table here that shows us predict good, predict bad, actually good, actually bad. We had our uninformed 40%, 60%. And so here we can calculate our priors here. And to calculate the priors here, we're going to take our uninformed 0, that's this place here. Uninformed 1 is this location here. And it's going to take this table and find the location of act good, predict good. So act good, predict good is going to be this 20% times the uninformed number here of 40%. And then what we're going to do is we're going to take the uninformed 40% times the act good, predict good, and add those two together. And then the other formula we have here, the uninformed section, the second one, so 0 and 1 locations, now we're in the second location, times act good, predict bad, plus our probability here, times the act bad, predict bad. So when you do that, it'll calculate those priors for you, 0.44 and 0.54, which we have just created. So then what we can do is figure out those 4 conditional probabilities of act good, predict good, act bad, predict good, act good, predict bad, act bad, predict bad. And to do that, we're using our Bayes formula, which then takes the probability here that something is good or bad times, right, that probability that they say that it is, I'll just go back to our formulas here so we can see what we're talking about, right? We're doing this calculation here in Python, and it's really just coming back to our Bayes here. We're doing the probability that's actually good times the probability we predict the good when it's actually good, divided by the probability that they predict the good, divided by that prior. So this is what you're doing here. Here's the priors, here's the uninformed, so the probability it's actually good or probability it's actually bad, times those conditional ones that we calculated. So when we do this, we get that the new probabilities for our decision tree are 72%, 41%, 15%, and 78%, which means we can then populate the rest of this. So going back to what we did before, which is B1, B2, B3, and B4 are those unknown probabilities in our decision tree. And so we can now repeat the processes we've done before. We have our activities where probabilities are values. It will fill in for us that B1, B2, B3, B4 based on our work. We create a table, our data frame, make this easier to see. And so we are now repeating the process we had with the other analysis. So create a table where the columns are activity, probability, and value, give them names, and then move the index activity over to be the index. Okay. So now we're showing our scenarios, not just the simplified version, but what we have now is we have that extra expert in here. And so if we go to our original decision tree, let's walk through it here from the beginning, which is we have a new product. If we invest in R&D, 30% likelihood, going to cost us $10,000. If we hire an expert, that expert's going to cost us $2,000. And that expert is going to make a bad prediction about the economy or a good prediction. If they predict it's bad, we can choose to do marketing. That marketing is still going to cost us $5,000. And then we have the issue here of it could be a positive economy or a negative economy. And we've now found probabilities of those positive and negative economies, given they predict it's bad. Or they make a good prediction. We decide marketing or terminate. If we market, it's going to cost us $5,000. After we market, it might be a good economy. So the probability that it's a good economy after they predicted it was good is 73%. That's what we just calculated. Or it could be that it's a negative economy when they predicted it was good and there was a 41% chance of that. Okay. If alternatively we don't hire the expert, then we don't hire the expert, the rest of this looks like it had before, which is $5,000 for marketing, 40% chance of a good economy, 60% chance of a bad economy. So we have populated these last probabilities here, conditional on the expert's prediction. So now we do the same process we had in our previous videos with our estimated monetary value. So we have our table of probabilities and values for all the activities. We populated all of them now. The zeros here are where the projects get terminated. The 5,000s are the ones where we do the marketing. The $10,000 is where we do the research and development. The $2,000 is where we hired the expert, and then the other ones are the outcomes based on good and bad economies and predicted good and bad economies. When we create our function for our expected monetary value, it gets way more complicated. So we have to go through our decision tree and look at all the possible outcomes. So 1835 is one path, 1836 is another path, 184 is a path, 2, terminating before research and development is another path. A1, A7, A9, A11, A13. So we're listing out all of the paths. So your function here is to list out all of the paths. And then once you do that, we need the probability of all the paths. Okay, so this is really just a replication of the code above with the change from value to probability. So we have all the probabilities of the paths and all of the values of the paths. So that means that we are then going to have it determine the expected monetary value by taking all 10 paths here and multiplying it times the probability of those 10 paths and then adding it all together. And I know it's a lot to output, but we could output all 10 paths and the probability of those paths so you can see how they change. All right, so then because that's all in a function, we need to call that function and have it output all of those items. So let's create our new function here. And that. And so here, if we were to output all this information just as a list, right, you get a big long list. So what we can see here is that given all this information, we can see that the expected value is $10,251. What we see with path 1 is it's $10,750, and then you can see other paths and how much they cost, and then the probability of them. So we no longer just have those couple paths, which means the probability now of that best case scenario is 3.6%. In terms of we do everything and we have a good economy and they predict a good economy. The most profitable is here. You can see some other scenarios here as well. This one here, notice this is $2,000 less than the first one here, and that's because we hired the expert for 2,000 bucks, and we get that good economy there, so it's 2,000 bucks less. So we can see based on this, it's worthwhile. We make $10,251 given all of the different scenarios and probabilities. We can see how sensitive it is to assumptions, so we can do the sensitivity analysis on the incomplete information. Okay, so what we can do here is we can keep the price where it is, keep the quantity where it is, but let's look at what is the likelihood that the expert isn't as expert as we think they are, they think they are. So you can see here, right? This 80-20 and this 30-70, we can actually change those and do an analysis here. And so we can keep the uninformed as 40%, 60%, keep the quantity as 3,500, 1,400, and the price as 35. But we could change that table here where we're looking at this relationship between predicted good and actually good and look at a range. So if I go back to the original table here, right, this was 80, 20, 30, 70. So what if instead of 80%, it could be 70%, 60%, 50%. They say it's good economy when it is a good economy. And then likewise, we can look at here, they say it's bad when it's actually bad. We put that at 70%. We could look at a scenario, and you can pick what you want to look at here. This is 70%, 60%, 50%. You could make it 70, 60, 50, 40, get rid of the 80 on the one end. It's up to you. So what you would do if you're going to do the sensitivity analysis with the expert's accuracy is that we would, inside of our loop, and we're going to loop through X and Y. So X is going to be here for the probability that they're actually right when it's good. So it's actually good when it's good. That's the AGG. And the ABB is actually bad when it's bad. That's where these came from. So what you see here is a loop where X is going to be the actually good when it's good. The Y is going to be the actually bad when it's bad. And we start by first creating that table where we have predicting good, predicting bad, and the actual good and actual bad. Because the other half of the table, recall, is just 1 minus and 1 minus, right? So we're just going to change that number and change that number and see what happens. Then we'll create that table. And then what we'll do is use that table to find the priors. So we've just taken that same line of code that we had before, and we're just going to put it inside the loop because we're going to pull from the new table that's created in each scenario. We then find the probabilities. So if we're going back to our Bayes here, we then can find the probability that we predict good when it's actually good, probability we predict good when it's actually bad. Those are the 4 probabilities for the decision tree, or we're trying to find the 4 probabilities from the decision tree based on probability is actually good, our priors that we calculated, and then the information that we're testing through our sensitivity analysis in our table. So we're trying to find those conditional probabilities for the tree. That's what this is here. And then it puts it into the table with the whole, it puts in the table with all the values, right? So the B1, B2, B3, B4 we had before is coming from here. And we're putting it into a table where we can call the pieces of the table using the function we've created that has all the different routes of the tree. Oh my goodness. All those pieces come together. Run it all. Turn it into a giant table. All right. Probability, it's actually good when it's good. It's actually bad when it's bad. So this is the accuracy of the expert. We can see how much this changes the expected monetary value. And we can see the paths changing. Here's the percentage for the paths changing depending on what's happening with the accuracy of the experts. So probability of path 5, 6, 8, 9, those are going to be dependent on the expert. And so then we can see changes in the valuation. And we can see in all these scenarios that we've given it, the estimated monetary value ranges from 10,000 to 10,500. Not a huge amount of change. So we're okay if the expert's not as accurate as they think they are. So if they're only accurate 50%, it's still going to make us money. Even though we're paying $10,000 for the expert, we're going to be making $10,000 to $10,500. We can plot this. So the last piece here is just to plot all this information. We're going to use that dot plot. Import plotly.express as px. We're going to use px.scatter. We'll call our table. We want the AGG, so actually good when they say it's good. We want our expected monetary value, and then our colors are going to be it's actually bad when they say it's bad. And we'll make the markers big. We'll make the x-axis say predicted good when actually good. And we'll have it be the expected monetary value, and the legend title is predicted bad when it's actually bad. And then we could add, do I add a line in here? All right. So we could add a horizontal line in here at 10,212. Just trying to remember offhand why I put one at 10,212. All right, so why the line at 10,212? Because if we scroll all the way up to the back to the beginning of all of these videos on decision trees, the initial scenario with no expert, where we predicted a 40% chance of a good economy, we had the expected monetary value of $10,212. So what we're trying to show here, if I go all the way back with our graph, is by adding that line at $10,212 is that was how much we were getting out of this project with no expert. And so we're coming down to the question of, is it worth hiring this expert to help with this incomplete information? And what we see here is that you can see some of the scenarios here where when they get to 50% accuracy in terms of saying it's good when it's good, or 50% when it's bad, those scenarios here, these blue ones, and even most of these purple ones where they can be accurate on where their accuracy is a little bit higher, they're not better than just not hiring the expert. So unless that expert really is able to predict the bad economy, notice these kind of salmon color ones are that it's actually bad when it's bad. What we really need is that expert to be able to detect a bad economy. It's okay. See, these are all about 50%, 60% when it's good. What we need the expert for is to detect the bad economy when it's bad. So we really care about a high level of accuracy to detect the bad economy, not so much about detecting that it's good when it's good. So we just need them to know when it's bad, to be able to flag that it's bad. There's more emphasis here on the bad economy than on the good economy. So should we hire the expert? Well, if there's an equally likelihood of all of these, maybe not. But if we can be more confident that the experts can find a bad economy or flag a bad economy, then they might be worth the money.